Hello everyone. Today I'll be presenting my coursework Android malware classification using machine learning. The research question. The central research question for this project is: can a machine learning accurately classify Android apps as a benign or a malicious using static manifest derived features? This question matters because Android is the world's most widely used mobile operating system, making it a major target for malware. Malicious app can steal personal data, track users, send unauthorized message, or compromise on device security. The traditional antivirus tools relies on heavily on signature, which cannot detect new, unknown, or heavily sophisticated malware. Machine learning provides a more adaptive, scalable, and faster method for malware detection. The dataset used in this project was 200 MD dataset containing 4464 Android application. The 200 MD stands for Traffic Based Unified Android Dataset for Robust Malware Detection. The version used here focus on static manifest feature. Out of 4464 apps, 3565 are malware and 89 are benign. Each app is represented using 241 static features extracted directly from its AndroidManifest.xml file. The feature include permission, API usage indicators, intent filters, and hardware access requirement. Because these features can be extracted with a running app, static analysis is safe, efficient, and ideal for large-scale machine learning. The dataset captures several types of static information that app request. Example, send SMS, read phone state, write external storage, etc. Methodology. The preprocessing started by converting labels into binary form, malware as 1 and the benign as 0. One invalid entry was removed and no additional cleaning was required because the features were already numeric. The dataset was split into training and testing sets using 60 to 40 stratified split, preserving the natural imbalance. Two supervised machine learning models were trained: random forest, which can capture complex nonlinear interaction between features, and logistic regression used as a simpler linear baseline for comparison. Both models were evaluated on same held out test to ensure fairness. The random forest model. The random forest model was chosen because it handles high dimensional data well and does not require feature scaling. It uses ensemble of decision tree, in this case 200 trees to learn and nonlinear patterns. A major advantage of random forest is feature importance, which helps interpret which permissions or manifest attribute contribute most to the malware detection. Logistic regression model. Logistic regression was used as a baseline. It is simple, interpretable, and efficient. Because it is linear and it cannot fully capture model relations between permissions and malicious behavior. Comparing it with random forest help us to understand how much performance is gained by using a nonlinear model. The model performance comparison. In terms of accuracy, both models have performed strongly. The random forest achieves about 99.16 accuracy, and logistic regression achieved about 98.13%. Although both are high, random forest clearly gives up the best performance, especially in detecting malware with fewer false negatives. The confusion matrix. The confusion matrix for random forest shows excellent result. It correctly classified almost all malware and benign apps with only a handful of misclassification. This is very important in malware detection because false negative missed malware are highest risk. The ROC curve. The ROC curve compare the probability outputs of both model. Random forest achieved a higher AUC, showing it is better at separating malware from benign apps across different threshold values. The logistic regression curve is slightly lower, showing it's reduced in sensitivity to complex feature patterns. Feature importance. The feature importance plot relieves which static feature had the best impact on prediction. The permissions such as write external storage, read phone state, receive SMS, and SMS alert window appear frequently in malware and therefore have high importance. This aligns with typical malicious behavior like accessing device identifiers, sending SMS message, or modifying the system. The correlation heat map. Correlation heat map shows the top 10 important features relates to each other. We see cluster of permission that often co-occur in malware, such as SMS permission and phone state permission. This reinforces the idea that malware tends to request coordinate set of sensitive capabilities. Limitations. This project has several limitations. Firstly, it uses only static features, so any behavior that activates at runtime, like network connections or dynamic payload, cannot be detected. Secondly, the dataset was imbalanced, containing far more malware than benign app samples, which can directly influence the model behavior. Thirdly, only two models were explored, advanced or hybrid models were not tested. What I learned? I gained experience pre-processing malware and training and comparing the machine learning models, interpreting the evaluation metrics like ACU and the confusion matrix. I also understand how permission relates to malicious patterns. I also learned how important nonlinear models are for security related classification tasks. Thank you.